All right, so this is section 6.40. We're going to finish up these notes. And question number 2. Let g of x be equal to the integral from 1 to x of 3t plus 5 dt. Find a formula that does not include integrals. Oosh. Part B, use your answer to find g prime of x. Ouch. Part C, what do you notice? That answer is going to be the easiest out of all of them. This is not an easy question to interpret. What does it mean and so forth? So this is one I really want to take you through. To begin with, we have this integrand, this function on the inside that says 3t plus 5 dt. Let's give ourselves a visual of that. Normally, our horizontal axis is x. In this case, it says integral with respect to t. So our horizontal axis is going to be t this time. Like that's our horizontal, side to side. And then the vertical is like the y. We're graphing this 3t plus 5 with respect to t. So think about that for a second. If you plug 0 in for t into this expression, wouldn't y come out to 5? Right? And then if I think about it even more, what kind of graph does this make? Just like the 3t plus 5. It's just a linear graph, right? What does the 3 represent? Slope. So it has a positive slope. It's going up something kind of like this. So the graph 3t plus 5 looks something kind of like this. And now I'm going to look at it from an integral perspective. The integral is the accumulator. It's the accumulation of the area under this curve. Going from t equals 1 to t equals x. Now, the upper bound is a variable. It doesn't say from 1 to 8, 1 to 9, 1 to even like going backwards like to -3. It says 1 to x. So 1 to x. And then again, the integral means find the accumulated area under that curve. So from here to there, we're supposed to find this accumulated area. It's going to pause for a second. Think about that, grasp that, talk to the person sitting next to you, if you will, if you have any questions. Does this representation make sense in the context of what we understand about those integrals? All right, little pause time, go.
Yeah, I know you just gotta find the area. Yeah. That's not that bad.
Okay, are we ready to actually find this formula for g of x that does not include integrals? So like what we're trying to do with this is find an area, right? That's what this integral is telling us to do. So let's find the area of this region. G of x is equal to the area of that. What kind of shape are we talking about here? Trapezoid. It's the average of the bases times the height. Okay, so these are the two parallel sides. These are the two bases. What is the value of this base? 8, right? Plug 1 in for the expression. So this base is 8. 8 plus. Now we need to find the length of this base. What is that going to be? Plug x in for the equation, 3x plus 5. So base 1 on the left plus base 2 on the right. What are we supposed to do with those to find the area of this trapezoid? Divide by 2, right? That's going to average them, and then multiply by the height, which is the difference between them, right? What is this distance? X minus 1, that's the entire distance, right? So times x minus 1. Write a formula for g of x that does not include integrals. There it is. Now, I'm going to simplify it a little bit because I can. Adding together, let's see, that's 3x plus 13 times x minus 1 all over 2. And then to multiply it out, it looks like 3x squared, I think plus 10x minus 13 all over 2. Now, to understand what we've done here, if I wanted to find the area under this curve from, let's say, 1 to 7, if I wanted to find 3t plus 5 dt, the area under this curve which is drawn going from 1 to 7, I could just plug 7 into this equation and find that area. Or if I wanted to find the area under the curve from 1 to 17, I could plug 17 in for that expression and have a really quick way to find that area no matter what the upper bound is. I could even go from 1 to say like -4, which would make it go backwards. And what do you think would happen to that value we'd be getting out of it then? It become negative because it's like you're walking backwards and you're accumulating negative area because all of those ultra thin widths would be negative values. But that's essentially what we've got right here. We have a way to find the area under this curve from 1 to any number. That's what we have. Part B. This is what g of x is equal to. Now I don't have it in terms of an integral because an integral can be kind of hard to understand, but g of x is exactly equal to this in a simpler form. So initially this looked like a really weird, confusing question, but if g of x is equal to this expression, use your knowledge of derivatives. What is g prime of x? So g of x was this. I can divide all those terms by 2 to maybe make it look like this. Maybe this looks simpler. What's the derivative of this first part? 3x. What's the derivative of the second part? And the derivative of the constant? 0. Because the denominator is just a constant, I could have done low d high minus high d low over low squared. I would have gotten the same answer. But this way is just simpler because the denominator is just a constant. If I did low d high, I would have gotten something minus the high d low. The high d low would have been 0, so it would have canceled out. We would have gotten over 4. It would have come out to the same value. I just knew this was going to be simpler because that was I can divide all these terms by 2. It made it just a little quicker way to find the derivative. All right, part C. Here's a chance to make a connection. What do you notice about your answer in letter B? Turn to your friend, go. And I'll tell you that this is no coincidence. This 3x plus 5, we basically saw it before, didn't we? It was the integrand we had up here, but now that variable has been substituted in for it. I could say that the derivative of this accumulation function, right, the derivative of this integral is just the integrand on the inside. I'll put it into the symbolic notation. We took the derivative with respect to x, so the derivative of this original. So here is our original function for g of x. When you take the derivative of this with respect to x, we got 3x plus 5. In other words, the derivative of this integral is the integrand. It's that function on the inside. Huge part here, we call this, it's called the fundamental theorem of calculus. And with that kind of name, it should sound pretty important. This is FTC, Fundamental Theorem of Calculus, Part 1. We're saying that the derivative of an integral is basically the function on the inside. Now, because of chain rule, we'll see that there are some slight modifications or updates we need to make to that. But that's our important idea number 2 here. We're going to say the rate of change. When I wrote down rate of change, what pops into your head? What synonym? Derivative. Derivative. Yes, the velocity is kind of, depending on the context, velocity is the derivative of position. But rate of change, IROC, instantaneous rate of change, the rate of change of an accumulation function What do we call the accumulation function? Integral. So I'm calling it the rate of change of an accumulation function is a fancy way, or another way of saying the derivative of an integral is the integrand. Yes. Integrand is the function inside the integral. So in symbolic notation, the derivative with respect to x of the integral from what does the lower bound need to be? In the problem we just did, the lower bound was 1. But did that really matter? No. It could be 0, it could be -5, it could be any constant. Upper bound is x. That is significant. These two variables are matching up with each other of some function. And I don't want to put the variable x in there too often, so I'm using a different variable just to not cross-contaminate it, if you will, of the function f of t dt is equal to straight up f of x. This is the fundamental theorem of calculus part 1, which is basically saying that the derivative of an integral is the function. Like add and subtract or inverse operations, right? If I have something, if I add a number and subtract the same number, we're back where we started. In this case, if we have a function and we integrate it and then take the derivative of it, we raised it and we lowered it, we're back to where we started at. They're inverse operations of each other. Only one example here. Let y be the integral from 8 to x of this function dt, find dy dx. Well, we could, though it would be very difficult, we could integrate this one, and we'll look at methods of integration later. Once we integrate it, then we could take the derivative of it. What do you think this would come out to? Quick turn and answer. What do you think it's going to be? And there it is. It's important, and it's usually going to be this way unless it's like a trick question. Taking the derivative with respect to x, and then we have that same variable of x up here. Those need to match up with each other. Occasionally, we'll see some examples where this is like x squared or sine of x. Then we have to get into the chain rule, and that's going to add just like another small layer to this one. We're not going to see many examples where the derivative is with respect to x, and we have a different variable up here like a theta or a w or something. Probably won't see any of those. In case we do, it's just something a little bit different.